Good morning, students. This is Meena Apati from Department of Computer Science, BLD Engineering College, CT. Today we are going to learn about the performance of the computer. In the previous classes, we have already covered about what are the fundamental units of computers, different types of computers, fundamental units of computers, memory unit, ALU, control unit. We also seen basic operational concepts in which we have seen how is the instruction being executed in the memory. So we learned about the connection between the processor and the memory, and we also learned about different types of bus structure, interrupts. So today we are going to learn about performance. Now, having understood the operation of a computer system, the next question is how good is the system? One measure of performance is time taken by the system to execute a program. That is how quickly it can execute a program. Now, which obviously should be as small as possible. The parameters which influence the performance are the performance clock speed, the type and number of instructions available, average time required to execute an instruction, memory access time, power dissipation in the system, etc. The performance is also influenced by the number of input-output devices connected to, the type of input-output devices connected, data transfer capacity of the bus, type and number of applications running on the system, and many such parameters. So another important factor is the cost of the system. A little improvement incorporated in the system should not result in too much increase in the design and development cost. So these are the main factors which are going to influence the performance of the system. In short, you remember three things, that is the hardware design, the instruction set, and the compiler. So I have tried to show you with the diagram performance of the computer. So processor time to execute a program depends on the hardware involved in the execution of individual machine instructions. So that's why we have the main memory, the processor, and we are using the cache memory to enhance the performance. The cache memory is situated inside the processor chip. So the processor and relatively small cache memory can be fabricated on a single integrated circuit chip, which can increase the speed. Of course, the cost also increases, so that it can improve the memory management. Now let's see processor clock. Processor circuits are controlled by a timing signal called clock. The clock defines regular time intervals called clock cycle, which I denoted by P. To execute a machine instruction, the processor divides the actions to be performed into a sequence of basic steps, such that each step can be completed in one clock cycle. The length P of one clock cycle is an important parameter that affects processor performance. Its inverse is clock rate. So R is equal to 1 by P, which is measured in cycles per second. Processor used in today's personal computers and workstations have clock rate that range a few 100 million to over a billion clock cycles per second. In standard electrical engineering terminology, the term cycles per second is called hertz, which I denote by Hz. The term million is denoted by the prefix mega, that is M, capital M, and I write as megahertz. And billion is denoted by prefix giga, which is denoted by capital G, and it is denoted as gigahertz. And 1250 million cycles per second is abbreviated as 1.25 gigahertz. Okay, 1250 million cycles per second will be now 1.25 gigahertz. Now the corresponding clock period for 500 million cycles per second, which is equal to 500 megahertz, will be equal to 1 by 500 mega, which will be equal to 2 nanoseconds. And similarly 1.2 gigahertz, or you can say 1250 million cycles per second, its clock period will be equal to 1 by 1250 mega, which will be equal to 0.8 nanoseconds. We now focus our attention on processor time component of the total time elapsed. Now that is, let's say, let T be the processor time required to execute. Let T be the processor time required to execute a program that has been prepared in some high level language. The compiler generates a machine language object program that corresponds to the source program. Assume that complete execution of the program requires the execution of n machine language instructions. The number n is the actual number of executions and is not necessarily equal to the number of machine instructions in the object program. Some instructions may be executed more than once, which in the case for instruction inside a program loop, others may not be executed at all, depending on the input data used. Suppose that the average number of basic steps needed to execute one machine instruction is S, where each basic step is completed in one clock cycle. If the clock rate R is cycles per second, the program execution time is given by the equation T is equal to N into S by R, and this is often referred to as basic performance equation. The performance parameter T of is important here. Now, how to improve the performance T? Looking at the equation, we can say that to achieve high performance, the computer designer must seek ways to reduce the value of T. That is, if the value of T is less, then the performance is better. It means that I need to reduce the numerator value, that is N and S. I have to reduce, and I have to increase R. The value of S will be reduced if instructions have smaller number of basic steps to perform, or if execution of instruction is overlapped. Using a high frequency clock can increase the value of R, which means that the time required to complete a basic execution step is reduced. So we must emphasize that N, S and R are not independent parameters. Changing one may affect the another one. Okay. Now, if say for example, a processor advertises as it is having 900 megahertz clock, it does not necessarily provide better performance than 700 megahertz processor because it may have a different value of S. So N, S and R are all interdependent.
Now let's see what is pipelining and superscalar operation. Normally the computer executes the instruction sequentially one by one. And improvement in performance can be achieved by overlapping the execution of successive instructions using a technique called pipelining. Pipelining basically increases the throughput of the system. The throughput is defined as the number of tasks completed per unit time. To increase the throughput, instruction must be available in advance. That is, next instruction has to be prefetched while the processor is executing the current instruction. This is possible only if a storage space is available for storing the instruction inside the processor. For this purpose, the processor maintains what is known as instruction queue. In a queue structure, instructions can be inserted from head end and removed from tail end. It is also known as first in, first out structure. For example, let's consider the instructions stored in the memory. Let's say we have, let me open, let's say we have, take here, okay, let's say we have two instructions in the memory sequentially stored. Say the instruction is add R1, R2, R3, and the next instruction is move R4, R5. Let us assume that both operations take 4 cycles. Both operations take 4 cycles, each for completion. The normal sequential execution structure would be like this, wherein I am trying to show 4 cycles. 4 cycles here. That is, say for example, T1, T2, T3, T4, T5, T6, T7 and T8. So the first 4 cycles will be taken by the first instruction, that is add R1, R2, R3, and the next 4 cycles will be taken by the next instruction, that is move R4, R5. Okay, so totally it will take 8 cycles are required to complete 2 operations. If we pipeline and prefetching the timing is done, we will require only 5 cycles. Now let's see how it can be 5 cycles. Let me put the clock cycles. Say 1, 2, 3, 4, 5, 6, 7, 8. 8 cycles are there. So the first instruction, that is add R1, R2, R3, it will take the first 4 cycles, and in the meanwhile, if when add R1, R2, R3 is getting executed, or the processor is able to fetch the next instruction, that is move R4, R5. This would look like this. Okay. So in total, while the first instruction add R1, R2, R3 is getting executed, the second instruction is fetched, and as soon as it finishes, the first instruction finishes the execution, the second instruction will be executed. So in total, it will take only 5 cycles to execute the 2 instructions. So while executing the add instruction, the processor can read the move instruction from memory. Thus, we can see that the first instruction is completed after 4 cycles. The second instruction will take only 1 more cycle to complete. Because the executions are overlapped in time, and if we continue this analogy, in sequential execution, a 4 instruction set takes 16 clock cycles, whereas with pipelining the time is reduced to 8 cycles. So this shows that performance rate is doubled. Thus, more number of instructions could be executed within small time interval, hence throughput is increased. It is important to note that individual instruction execution time is not changed, but the overall execution time is reduced through partial overlapping the instructions. Right. So this is how pipeline works. Now, the thing that we need to remember in pipelining is instructions are not necessarily executed one after the another. The value of S does not have to be the number of clock cycles to execute one instruction. Pipelining, it overlaps the execution of successive instructions, as I have already just now shown you with an example, that is add R1, R2, R3 and move R1, R5. Both can be executed in 5 cycles. Now, superscalar operation. Now, what is superscalar operation? Now, in superscalar operation, multiple instruction pipelining are implemented in the processor. So, what is the main goal? The goal is to reduce S. So, what is S? I hope you people remember that it is the average number of basic steps needed to execute one machine instruction is called as S. Okay, so we can reduce S by using pipelining and superscalar system or superscalar process. Now, usually computers which have this mode of fast operation like superscalar, um, now we have seen already how to reduce S. Now let's say how to reduce or how to improve R. There are two possibilities for increasing the clock rate R. First, improving the integrated circuit. First is by improving the integrated circuit technology that makes the circuit faster. The another way is to reduce the amount of processing done in one basic step. However, this may increase the number of basic steps needed. Now, increases in the value of R that are entirely caused by implementing integrated circuit technology will affect all aspects of the processor's operation equally, except the time to access the main memory.
So in the next video, we will see about the CISC and RISC, or the compiler, and some performance measurement equations. Till then, please read the textbook. Take care. Goodbye.